Right, we're going to start now something else, and that's the processor manager. And the processor manager obviously everybody knows what the main job of a processor manager is to take care of the processor and allocates it to the different processes or programs that need it in the most efficient way, and it must also follow a policy that's laid out in advance for the processor manager by an IT manager. All right, so generally, as the process goes in, it passes through a number of stages, and we call them number of states. So just like a student maybe about to start to go to college, before they even start studying, they're kind of a new student. They haven't even been given acceptance, then they came in or inquired. And then once they start studying, they might go into a different state. They're a real, regular kind of student. And then hopefully when they finish all their exams, they're still a student, but they've kind of finished and waiting to graduate and leave college. So these are different states a student passes by. Similarly, with a process, as a program comes through the execution process, from the moment you double click on that icon, the stages start for the execution of a program, and goes through a number of states or stages. And here they are. The first stage a program goes through is known as a new stage or a new state. So a program in a new state is received by part of the processor manager. In fact, the processor manager in most computers or most operating systems, it will probably split itself into 2 or 3 sections. And the main task really of a processor manager is scheduling. That's scheduling the processor. So what does that mean? It means who's going to use it. You use it next, and then you're next, and so on. That's scheduling the processor to the processes that are there that want to use it. So that's really its main task. It schedules it in the most efficient and the best way. So if a process comes in, when you click on a program, the program comes to the operating system, and the operating system calls the processor and say, here's a program that we need to run. You're responsible for the CPU, so I'll start taking care of it. So first thing it does for it, as maybe a new student about to start registering for a course, or a new patient arriving into hospital, so there's a stage there where we take that and create or find out more about this process or this individual. And we also create a small label, just like a file is created for you, or a record when you want to register into a school, or when you go into a hospital, you open a file for a patient, and they must give you a patient number, or a student number, or some number. Why? Because sometimes you get 2 people that have the same name. A name cannot be used to identify individuals. And same with processes. So when they come into this system, they give it an ID number. So every program that comes in, it's given ID right here at this stage by the processor manager. And which part of the processor manager? The processor manager has 2 parts. One of them is known as the high-level scheduler. And we have a low-level scheduler. So we'll deal with it here. So we have 2 parts. So the high-level scheduler looks after any new processes that come in. Just like in a college, for example, there is a department, registration office that takes care of new students, and when they are finishing and graduating. But once they are here, they hand them over to the faculty that takes care of them. So same here. The high-level scheduler deals with new students and with finishing or ending students. Let's say finishing processes. So they call them finishing or finished process. So if the process is starting or finishing, then it's taken care of by part of the processor manager called the high-level scheduler. Right, what happens to it? You need to know what happens at each stage to a process. So at the new process, the process is given an ID, unique ID. And it's given a priority. Because sometimes we handle processes based on their priorities. Like two processes want the printer, we might tell the manager here, the device manager, give it to the one with the higher priority, maybe. So, but it's used in all systems. Also, we need to find out, is this process a CPU bound or IO bound? You heard of this? But in our first week or second week. Anybody knows what CPU bound means? CPU bound program. Any idea? You know what CPU bound program is, or IO bound program? So it's a program, IO bound program, it's a program that needs a lot of IO and very little CPU. And a CPU-bound program is a program that needs more or a lot of CPU and little I/O. Why does that make any difference? Yes, it does. It makes us be able to use, if you have lots of users, lots of customers. For example, you're managing some place that has, remember the game places where you have a pool table and you have a table tennis table. And if you have customers coming in, you better off bringing two that love pool and two who want to play tennis, or else everybody will be queuing. If everybody wants to play pool table, then nobody will be using our table tennis, for example, and the pool table, everybody's waiting behind it. Only one or two users are using it, and the rest of them are sitting waiting. So this is a technique used by all operating systems. Try to figure out, is this program and needs a lot of I/O? Maybe the next program after it also needs I/O, says you wait for a little while. Another program needs CPU bound, say you two go. Because this guy wants more CPU and this guy wants more I/O. They're both happy. This guy is using a lot of printer and hard disks. This guy is using a lot of CPU. Of course, every now and again they need a bit of the other in return. So this way we keep our customers both busy working, and all our resources are being used. So that's the idea of classifying our processes between CPU bound and IO bound. It also finds out the size of the process and the type. Is it maybe interactive kind of process, or is it one of those processes that doesn't need any interactiveness? And so on. And does it need any files? Does it need any devices? How many files, how many devices? So it keeps a list of all these. And it writes all these things in kind of a label. They call it Process Control Block, PCB. So they write this in something called PCB. It's just like a file that's open for you, where maybe it's important to have your name, date of birth, address, phone number, things like that, details that the college needs from a student. But here, these are the kind of information we need, and they're written in something called PCB. That's created on the spot. So PCB is not a file. It's something that stays in main memory. So they call it a data structure. So if you're asked what's a PCB, it's a data structure that's created. When is it created? At the new stage. When a process comes in, we create a PCB for it. Every process comes in, we open a new PCB for it. And when it leaves, we'll be destroying it or discarding it at that stage. So as long as a process like you, as long as you're here in the college, there's a file. Every time you pass a subject, they write that information. Every time you fail a subject, every time you do something good or something bad, they probably write it in there. So same with this PCB. Everything happens to a process. It says, I need to open a file. Yeah, we write it here right now. It's reading file record number 17, maybe, and so on. So that's called the PCB. And remember, when we say the process is moved to another queue, we don't move the process. We don't move the code. The code goes in memory somewhere and sits there. It's this PCB that gets moved. Okay, so it's the PCB that actually moved from one queue to another. This is for programmers to know. Like when you say, oh, this process is going to put it in the printer, it needs to print, put it in the queue for the printer. We don't put the process, we put its PCB that goes there and hangs there. Just like if you see flight controllers at the airport when they're talking to airplanes and they have these little samples of airplane, little blocks, and each one has the flight number, and they say, oh, move to 28,000. They move it. They actually box, they put it up there on 28,000. So they're not moving the airplane, they're moving this thing that represents the plane. Same here. We're moving the PCB. The code is, once it goes into a page, it stays in a page unless we have to remove it. So that's a PCB. So if you ask, now you know what a PCB is. When is it created and when is it deleted or discarded? And what it contains. And who creates it? The high-level scheduler creates it. And then the next job, the high-level scheduler starts passing these processes to the next stage. They say, okay, now you're ready to go in. Just like you're a student, you finish your registration, you can go into college. And we call this ready. This is the ready state. The process is in the ready state. Ready for what? Ready to run. Ready, if it has the CPU, it will execute. It will start executing. But right now, when a process comes in, it's still asleep. And we create a label for it, or we put it on it, and we classify it. Are you a CPU bound or IO bound? And how big is this process? And we give it an ID. Still nothing. That CPU, that process is not running, it's not executing yet. And then by the time we put it in the ready queue, it still hasn't run. And the ready queue is just like a queue. Usually first in, first out. So it just joins the end of the queue. It could be maybe a priority queue. We put it in the front. Or sometimes they have 2 or 3 queues. High priority queue, medium and low priority. So it's put in the right queue for its place. But somebody's going to get out of the queue and get to the CPU. So that's what happens next. This is the running state. This is the only time a process really runs. Let me just start that attendance thing. I don't know if it's started. Is it started? Okay, it should be running now. Right. So now, if a process comes in right at the start, we call it, it's a new state. It's identified, it's given an ID, it's classified based on many things. A PCB is created, its requirements of input or output, like files, devices, are identified. Sometimes say, oh, we don't have this. Maybe a process needs 3 printers. We're sorry, we only have 2 printers out. But everything is okay. We move it to the ready state. We try to move I/O bound and CPU bound together, so they will use all the system resources. It stays in the ready state until it gets its turn to execute, to run. So now, this is where the CPU is. Once the process goes into the CPU and starts running, we call it the process is in the running state. So that's really CPU time here. CPU is executing this process. And we know every program will run and by itself will request some input or output. This process will say, I need to read something from a keyboard, from a file, from anywhere, from a communication line, or I need to produce something or write something on a printer or display something on a screen or a scanner. So whatever input or output device, then it stops. Anytime any process or program wants to perform an input or output operation, it's not allowed to do it. It's put asleep, and we move it to another state, and we call it what do we call this state? The blocked state. There are different names for those, so we'll look at the different names later. Blocked state, that means this process is being blocked while work is being done on its behalf. And it's put into a queue. One of those queues, there'll be dozens of queues. There'll be a queue for a printer, or a queue for keyboard, or a queue for a scanner, or a camera. So there are lots of different devices, and each device has a queue. Maybe the queue is empty, it will be served immediately. And then, but the process is sitting in a blocked state. It cannot continue until it reads, maybe from a hard disk, a file. It needs to read something before it can continue. Once that job is done, whatever it was waiting for, reading a record or printing something, once it's finished, we move the process up to the ready state. That's the one that will be moved. That is the process. That's the one that will be moved. It's like maybe in the office, maybe in a college, they might have few offices or officers, one who looks after first-year students. So all your file and cards are given to that individual. And then you pass first year, you want second year. So they might take all your files and move them in the office to the second year. So they say, oh, we moved this student to second year. They didn't move you, you're already somewhere studying, but they moved your card or your file. So that's exactly what we are moving. We're moving this data structure that's called the PCB. So we move the PCB back into the ready queue. So this is a queue sitting here for ready. What's the guy in the queue here waiting for? Waiting for the CPU to be available. And this part, those movements from here to there, this keeps happening all the time. So every program goes to the CPU, run for a little while, say, I need another record. Move it here to the hard disk, read your record, it's brought to the ready queue. Wait until the CPU is there, ready. It's moved there, it runs and keeps doing that for a number of times. It could be hundreds of times, it could be dozens of times, we don't know, depending on the program. And sometimes, guys, a program gets into the CPU and just runs and runs and runs and doesn't ask for I/O. That's not good. That's not good for the rest of them that are waiting. Especially if the rest of them that are waiting are interactive processes. That means this guy's going to delay them. It's like going into a supermarket queue and you get stuck behind somebody with a huge trolley full of stuff, piled up stuff. You're going to be there for 10, 15 minutes instead of finishing in 10 seconds or 15 seconds. Same here. Sometimes a process just gets into the CPU and never stops and never asks for input or output. That means it doesn't give up the CPU voluntarily. So what they've done for those kind of processes, they introduce something and they call it the quantum. And the definition of the quantum is the maximum amount of time a process is allowed to use the CPU. For example, let's say in the CPU terms, maybe 100 millionth of a second. But let's say in our terms, you use your mobile phone, we say you have a quantum 5 minutes. After 5 minutes, if you don't stop using it, we'll take it from you. We give it to someone else, we'll pass it around, not your phone. But if we only have one mobile phone and we keep passing it around from one user to the other. So we put a quantum. The quantum is the maximum amount. You can give it up before the quantum. But the quantum is like a timer that every time the low-level scheduler takes a process, puts it in the CPU, and starts that quantum timer. So the process is running and the quantum is ticking. If the process says, oh, I need input, then we'll take it out and we switch off the quantum. If the process doesn't ask for input or output, it means it doesn't leave the CPU, the quantum will give us an alarm, quantum oh. Then we call a quantum handler that comes and takes whoever is in the CPU, move it. But it doesn't need I/O. They don't send it to the input-output. What they do, it just needs the CPU. They say, go back to this ready queue. Go back to the ready queue. So as you can see, if a process is running, there's a possibility it might leave for an I/O or it might leave for a quantum because of a quantum. Goes back to the ready queue. So it's like somebody takes too long to using a common resource. We interrupt it at a certain time, we put them back at the end of the queue. You'll get your turn again, but you have to give the others a chance. Yeah?
It goes back to the ready queue. Does it have to restart or do you pick it up or not?
Every process when it gets to the CPU will start up where it left off the last time. It doesn't have to repeat, no. All right, let's just go through the rest of the stages and then we get to this process. So now, do you know what a quantum is? Yeah, what's a quantum? It's the time a process is allowed. It's a good answer, but it's not the right answer. What's a quantum?
The maximum amount of time.
Maximum time. The key word is the maximum time. Yeah, now finish it. You got the first word right.
For a program to use CPU.
Do we still call it a program?
Process.
A process, yeah, would be a better word. Okay, so a quantum is the maximum time a process is allowed to stay or use the CPU, and if it exceeds a quantum, it will be interrupted. Right, okay, and then when eventually this process, we go around many times between I/O ready, run, I/O ready, run, but sometimes straight to ready, run, and then I/O again, or blocked, ready, run. Eventually, it will finish. Eventually, it will get to the last line of code, and it will finish, and it will go into the finish or terminate state. Some books call it terminate, some books call it finished. Finished state or terminate state. So, sometimes it commits an error that makes it, oh, we must interrupt that process and terminate it. Some errors, while a process is here running, there have some kind of errors that will cause the interruption of the process. Anybody can think of an example? What kind of error would make a process be terminated? Anything to do with memory? Anybody remembers anything to do with memory?
Divide by 0.
Say it.
Divide by 0.
Division by 0 is only one thing. If your program ever says divide x divided by y, and y has a 0 in it, then that's a no-no. That's illegal in computing, to divide by 0. Your program will be terminated. What's the other thing?
A process is trying to access the memory allocated to other processes.
If a process tries to access or reach memory that doesn't belong to it, it belongs to the operating system or it belongs to another process. That's another kind of error. So going from the running state to the terminating state can be due to normal finishing, just finished everything, or due to an error. A process is terminated, did not finish by itself, it just had to be terminated. And those are two examples we had. Division by 0 or trying to access memory at the wrong, wrong memory, not yours. So all this part here, down here, this cycling around those three states is done by the low-level scheduler, and when a process is brought into the finishing state by the low-level scheduler, what happens to it there? So remember, a process here coming in, it's given memory. It's allocated memory by the memory manager. And that's also one of the information kept here. Where is that memory? And also, so when it goes to the finishing state, any process goes to the finishing state, the operating system will be calling the memory manager saying, hey, come on, this program is finished. So take your memory, do deallocation. And for the processor manager, it will also do a number of things. And for every, like the device manager, we will talk about device manager in the future, if it had a hard disk or a printer allocated to this process, then the device manager will take a deallocation. And what else? In our system here, in the processor manager, remember, the PCB was created here at the new state. At the terminating state, we will be discarding this. But before we discard it, there's a lot of information in it. What kind of information? Every time this process went into the queue, we write down what time it went into the queue and how long, what time did it leave it. And then every time it goes to the CPU, the schedulers will write in the information in the PCB what time it got to the CPU and what time it left it. So they keep totaling up all the different times. The time it was in the blocked state, the time was in a waiting state, waiting for the CPU that's in the ready queue or the ready state, and the time it's spent in the CPU. And could anybody tell me, where's the turnaround time? The time from which state to which state there? Anybody remembers turnaround time, yeah? From new to finish. So when a process comes in new, we create PCB and we write the time it arrived. And when it's moved to the finished state, we write the time it's reached the finished. And that would be the turnaround time. You can also calculate the CPU time or the run time. You can also calculate the waiting time for the CPU. Remember, this one, they used to call it waiting and blocked. But it's not the waiting time. That's, even though it's blocked, it's doing nothing, but a printer is working on its behalf. But here, nothing is working on its behalf. It's waiting for the CPU. It's doing nothing. And that's what we call waiting time. Waiting time is the time spent in the ready queue, waiting for the CPU. So remember, when you run your program, it's not all the time is running time. That's the turnaround time, but it includes waiting time, it includes CPU time, and it's calculated accordingly. And the information is kept updated in the PCB. Every time it gets the CPU, it's updated here, and every time it leaves it, it's updated. So, and then when we get to this stage, all this information is extracted, and usually by all systems, they keep them in a log, a file that shows all the programs that ran, what time did they start running, what time did they stop running, how much CPU time did they use. They use it for accounting information. And maybe also they use it for debugging information. If a problem happens and we find a file is missing, can you show us, in there, and you'll see who opened this file. So this will also include all files left, opened, read, modified. It will all be written in the log. So once all this information is written to permanent storage, we can delete the PCB. And of course, any files that are open, they'll be closed. The file manager will come and deallocate them, take the files. The device manager will take its devices. Memory manager will take its memory, and we take the PCB is removed, and the information is written. That's what happens at the finishing stage. Okay, quick question now. Name one condition where a process is happy using the CPU, and the next day it doesn't use the CPU anymore. Give me one reason why, or where could it have gone? On the diagram there. CPU is where the running state is. Where does the process go from the running state? Okay. Let me pass the question to someone else. And listen to the question. Right. A process, are you with us? No. Okay. A process is running in the running state at the CPU. The next moment of time, it's not at the CPU. Give me one place where it could have gone, and why. No, it's going to go into a blocked state, or a ready state, or a finishing state. What did he say? It could go to a terminating state if it finished. Right? Yeah. So if a process is running right now in the running state, and then a moment later it finished, it will be moved, it will go to the terminating state. Give me another possibility. Where else could it go? If I am a process here running, jump to the terminating. No, where else could I jump? The blocked state. Why would I go to a blocked state? Why would a process go to a blocked state? If it needs an input or an output, it will be moved to a blocked state. Do you know where else it can go? We have a running process there. Once it went to the terminating, once went to the blocked. It can go to ready. Fantastic. What would bring it to ready? No. Why would a process go from the running to the ready state? If you don't stop talking, I'll ask you to leave. If you're not interested, either stay quiet or go out. Take your attendance and leave. But don't stay and cause more chaos here. Who was talking? No, I think it was you. It was you. He gave you the wrong answer. He said, why would the process go from the run to the ready state? If it spends so much time and exceeds what level over time? The quantum. So if a process spends a long time in the CPU, it will be moved back to the ready state, right? And what's the length of that time called? That's quantum. Is that what you said? Okay, good. Guys, you don't have to answer, but it will help. I'll know you're okay. You're with it. You understand what's happening. Right. Okay, what else would, give me another reason why a process would go to the finishing state or terminating state. You. A process is in the running state and it's gone to the terminating state. Why? Oh, it finished? Yeah, that's one reason, yeah. Good. What other reason?
If there is an error can occur if not suffice to use or again.
So if it's terminated, not finished by itself, it was terminated because it committed an error, right? Now give me one kind of error why a process might be terminated and moved to the